Here we can see another pulse signal that we want to measure. Again, we can analyze its spectrum and overall acquisition time, and we can even see the pulse table and the overall measurement time. And we see some really interesting artifacts here in the amplitude versus time measurements. But again, we can just look at the signal of interest. In this case, we're centered at 1 gigahertz with a span of just under 40 megahertz. And we see a spectrum that has some interesting lobes to it. On top of that, as we initially mentioned, we see something that kind of looks like noise in the amplitude as well. So there's a couple things we might want to do to be able to analyze this signal better. So one thing that we're going to do is we're going to add a trace. So let's go trace, and then we're going to hit the plus button here, and that's going to add an extra trace. And I'm going to drag this over and put it at the bottom of the amplitude measure time. And I'm just really intrigued on what might happen in terms of phase information. So let's change this trace data to phase measure time. And it looks like it's a little off scale, so I'm going to right click on the trace and select auto scale. And we can see there's some interesting slope trace phase artifacts here. So I'm going to select my zoom windowing button here, and I'm going to zoom in on the second pulse with that and say scale X and Y. And I can see that this is phase versus time. And so I'm going to select a marker, and I'm just going to use my marker to see what happens here. And I'm going to have my marker over time. And it really looks like it's really switching between two main phase states. So I'm starting to think that this might be a binary phase shift key pulsed signal. So I'm going to right click and hit auto scale, and that kind of brings me back out to this larger view. I'm not quite sure why there's some slope issues here. Could be a lot of different things, but let's just try to identify these pulses. I feel comfortable with the amplitudes we're measuring here based on all our setups from the pulse properties menu of pulse detection and time and regions and advanced. But something I want to go into a little bit more is this analysis function. In here, we have this modulation tab, and right now, we don't have any pulse modulation detection turned on, but when we're not unsure of the modulation, we typically just classify it as CW, which is fine. But I want to click CW because in worst case, if it is, we're still correct. But based on these two phase states, I want to select BPSK as well to see if I'm able to get a BPSK measurement. So with that, I'm going to take another single shot measurement, and nothing changed, which is interesting because if it was CW, I shouldn't have phase changes here in my measurement time. So I'm going to go back to my pulse properties menu and go back to analysis and modulation. And I'm going to enable custom BPSK. And the reason why I'm doing that is because if it's truly 0 to 180, or that kind of standard BPSK where you're on just the x-axis, I would figure that would have been detected. But in this case, I have a hunch that it's about 160 degrees. So I'm going to select 160 degrees and update my measurement once again. Again, nothing. Let's do one other thing here. I'm going to go to pulse properties, and again, I'm going to enable extended bits, and that did it. Now, the reason why this is important is because previously we were only able to measure BPSK signals of up to 10 chips or 10 phase changes, whereas now we can measure up to 1,024 phase changes. So something I want to show is if we take our zoom tool and zoom back in like we saw before, we see there's a lot more detected phase states now than what we initially saw. And in this case, we have quite a few. And we actually report the number of those. So in our pulse table, we can see that pulses 1 through 6, 1, 2, 3, 4, 5, 6, are represented here. We detected them as BPSK, but we also display the chip count. Right now they're showing 45 chips or phase changes for each pulse. Something even more interestingly, we can change one of these traces to the result table and then to demod bits. And so now we can actually see the ones and zeros of that particular pulse. So this one is reporting pulse 1. And so what we can do is we can take our zoom tool and just zoom in on pulse 1 and really analyze its phase and see here it should match up with what we see here. So 0 1 0 0 0 1 1 1. So 0 1 0 0 0 1 1 1. So there's a whole frame of BPSK chips that we could measure, and we could even step through that if we wanted. Something also, you could put a marker on one of these as well as on the phase trace, and then select markers, couple markers. And then as you go along, you should be able to update where those phases are on all the traces. So that's something that's really powerful to be able to see what's going on from a phase over time within not only the amplitude, but also the phase itself. So this is a really powerful way to validate is your signal of interest having something that's a little bit more that meets the eye in terms of modulation. And this kind of thought process can be applied for any one of these, whether it's linear FM, triangular FM, Barker codes, Frank codes, QPSK, or even P codes. And you could even have these all turned on. And if you have them all turned on, you'll see that we capture it just fine. So you should be able to detect any one of these types of modulations on pulse moving forward. So something really powerful within the Keysight 8900 VSA pulse analysis software. Really urge you to explore this a little bit more to be able to understand not only custom BPSK phases instead of 0 to 180, but anything in between, but also in extended bits for really long BPSK and even QPSK chip counts.